starting with our chapter 7. Okay, so I did chapter 7 with you guys while we were functioning in the classroom, but I will go ahead and start it here again. So in this chapter, excuse me, we're going to learn about quantum theory and atomic structure. We're going to be learning about the nature of the light, atomic spectra, the wave-particle duality of matter and energy, the quantum mechanical model of the atom. Excuse me. So if you look at the nature of the light, light is a wave, right? So it's going to be something like this, like a wave. So the visible light, which is the light that we see, it is a type of a electromagnetic radiation. And we can describe this wave by three variables. One is called the frequency, and then given the symbol nu. And then we have wavelength. Wavelength is given the symbol lambda. Wavelength is the distance from one place to another one. So this is just one wavelength. And then we have the speed, which is the distance it moves per unit time, given in the units meters per second. And then we have amplitude, the height of a wave crest or depth of a trough. This wavelength and frequency has a inverse relationship. So the speed of light would be frequency times wavelength. And then the constant c is 3 into 10 to the power 8 meters per second in a vacuum. And this is a wavelength. And you can see the relationship of frequency and wavelength. So there are three wavelengths. So the first one, which is A, has the longest wavelength, and B middle, and then the C would be the shortest wavelength. And the frequency is the cycles per second. So if you look at the three, C would have a higher frequency. Okay, so the lambda, which is your wavelength, and frequency has a reciprocal relationship, meaning lambda is inversely proportional to frequency. And then if you take wavelength and frequency in one side, we can say that is a constant, which is the speed of light. Okay, and this graph shows the amplitude of a wave. So the high amplitude would be a more brighter light, and then the low amplitude would be a more dimmer light. And this is the electromagnetic spectrum. Excuse me. Visible light is what we can perceive with our naked eye, which is the white light separated into 7 different colors. And you can see the wavelength range for the visible light is 400 to 750 nanometers. Just below the UV visible light is the ultraviolet. You can see 400 is the violet. So the colors are Vib, Gior. And I know you guys are familiar with Roy G. Biv, but you can also think of it as Vib, Gior, violet, indigo, blue, green, yellow, orange, red. So violet is where we have the 400, and right before violet we have ultraviolet. So VV goes together, and then right before that X-rays, and then we have gamma rays. And right after red we have infrared, and then the microwave and radio waves. You can see wavelength increases. You see wavelength increases going from gamma rays to radio waves, and the frequency increases going from radio waves to gamma rays. So you can see as the frequency increases, energy also increases. We know gamma rays and X-rays, they use for chemotherapy, in the sense radiation for cancer patients. So they have high energy beams. And radio waves we all access in day-to-day life, which is much lower in energy. Okay, as the frequency increases, energy increases. Excuse me. We also looked at this problem in the class. Dental hygienist uses X-rays and the wavelength is given as 0.5 angstroms to take series of dental radiographs, and the patient listens to a radio station. Wavelength is 325. Looks out the window at the blue sky, lambda 473. And it is asking what is the frequency in per second of the electromagnetic radiation from each source. Assume that the radiation travels at the speed of light, 3 into 10 to the power 8. So we are given wavelength. We also know speed of light. So we can use the equation C equals wavelength times frequency. So then the frequency would be C over lambda, wavelength. And what we need to remember is speed of light is 3 into 10 to the power 8 meters per second. So wavelength has to be in meters in order to convert it to frequency. Okay. So this is how we're going to perform our calculations. So the first one, wavelength, is given in angstroms. So you are hearing angstroms for the first time. 1 angstrom equals 10 to the negative 10 meters. So you can that conversion to convert angstroms to meters. And then you use equation frequency equals C over lambda. So speed of light 3 into 10 to the power 8, and then the lambda in meters we just found out. So this will give us the frequency. And for the radio signal, speed of light is given, lambda given in 325. So we're going to convert it to meters. 1 centimeter equals 10 to the negative 2 meters. Okay. That gives us the frequency for the radio signal. And for the blue sky, wavelength is given in nanometers. So we can convert nanometers to meters. 1 nanometer equals 10 to the negative 9 meters. And you use the same formula, frequency equals speed of light over wavelength. That will give us the frequency for the blue sky. Okay. So this slide explains behaviors of waves and particles. What are the differences? So the first one you can see, electromagnetic radiation travels as a wave. So one of the behavior of the waves is once it reach to a different phase, it bends its angle. So you can see angle of refraction is right there. It changes immediate. It's not a gradual change. It's immediately. And we call that phenomena as a refraction. That is a behavior of a wave if it meets a different surface between air and water. And if you look at a particle doesn't do the same thing. It changes the speed gradually. Okay. Another difference between the waves and the particles, if you have waves and it reaches a slit and it's going to bend around both edges of a small opening, forming a semicircular wave, and we call that as a diffraction. And for a beam of particles, some of the particles will enter, some will not. It will not form semicircular formation like waves do. Formation of a diffraction pattern. If you have two slits, if a wave passing through two slits, you can have two different semicircular formations. And some of these waves will be in the same phase, where we call it as waves in phase, and then it would produce a brighter light, these white ones. And some of these waves would combine in opposite direction. If they are combining in opposite, that we call it as waves out of phase, it produces a dark region. So that is a diffraction pattern, your bright light and the dark light. And this is actual picture of two waves. Okay, so you can see a diffraction pattern. So we know wave can have a frequency, wave can also have a wavelength. And we can also relate frequency and wavelength to energy. Observation that led there is a correlation between energy and the frequency is called the black body radiation, which is a solid object emits visible light when it is heated to about 1000 Kelvin. You guys have seen this one. When have you seen these ones? I'll show you in the next picture. The color and the intensity of the light changes as the temperature changes. Color is related to wavelength and frequency, while temperature is related to energy. You see, if you heat more, meaning it increases the energy. I remember heat is a form of energy, heat and work. I hope you remember from our thermodynamic chapter, right? So if the heat increases, meaning if it increases energy, and you guys have seen when you cook, when you turn on your stove to a higher temperature, the coil can become red in color. As you increase the temperature, meaning increase in the energy, so you start seeing a color. So the color is related to frequency and wavelength. So there is a correlation between energy and frequency and wavelength. Explanation: energy is therefore related to frequency and wavelength. Okay. So energy is related to frequency. As the frequency increases, energy increases. And then the constant for that is called H, which is the Planck constant. And here you can see delta N. N is a whole number if you are looking at a different number of photons. Okay. Also, by using this equation, you can find out the change in energy. So energy proportional to frequency, and energy equals N is a whole number. It could be a positive integer, and H is the Planck constant, and then nu, NH nu. Energy and frequency are related. So these are some familiar examples of black body radiation. Smoldering coal, electric heating element, and light bulb filament. As you increase the temperature, you can see a color. Okay. Quantum theory of energy. Any object can emit or absorb only certain quantities of energy. We call that process as energy is quantized. It occurs in fixed quantities rather than being continuous. So that each fixed quantity of energy is called a quantum. Atom changes its energy state either by emitting or absorbing one or more quanta of energy. Okay. And again, if you want to find out the difference in energy, we can use delta E equals delta NH nu. Two different states of energy levels. We can use this example. The photoelectric effect. What is the photoelectric effect? It is, let's say you have a photon of light coming. So H nu is the photon of light. You see H nu right there. And then once it hit the metal surface, the metal can eject an electron. And that ejected electron or the freed electron, it can travel to the electrode and then it can produce a light. We call that effect as the photoelectric effect. Okay, so let's look at how we can use this energy equation, and then the lambda and wavelength and speed of light to interconvert energy, wavelength and frequency. A student uses a microwave oven to heat a meal. The wavelength of the radiation is 1.2 centimeters. What is the energy of one photon of this microwave radiation? We are given the wavelength and we want to find out the energy. Okay? We don't have an equation where we can directly relate energy and wavelength. But we have this equation that we know. Energy equals h nu. But nu is the frequency, h is the Planck constant. We don't have lambda over there, which is the wavelength. But what we can do is we know C equals wavelength times frequency. So we can rearrange this equation. Go back. So that will give us frequency equals C over lambda. Right? So energy equals h times nu. So we can write energy equals h. Instead of frequency, now we can write C over lambda. That is the equation that you are seeing over here. Energy equals h nu and energy equals hc over lambda. H is a Planck constant, which is 6.626 into 10 to the negative 34 joules second, and c is your speed of light. And then you can divide it by the wavelength given in centimeters, but you want to make sure that you convert it to meters. Okay, 1 centimeter equals 10 to the negative 2 meters. That will give you energy as 1.66 into 10 to the negative 23 joules. Okay, all right, so I will end our first session over here. That's about 15 minutes. So I'm going to make it a small videos, so that way you don't have to keep your attention for a longer time. All right, I'll see you or meet you in the next one soon. Bye-bye.